Okay, so let's start. So originally, this talk was supposed to be about the Boudin-Fourier theorem, which I've spoken about, but I'm still trying to understand in some way. And but a couple of days ago, I discovered there is another huge subject about polynomials that I didn't know about. So everyone learns in preschool or somewhere the NYNTS-Mel, which says if you have polynomials, F1, F2, some set of polynomials, let's say with complex coefficients and variables, and you look at the set of all A and Cn such that f to the I of A is 0. So all roots of simultaneous roots of these polynomials. So you have this affine variety, and sometimes it's empty and sometimes it's not. And the Nathanson-Polya says that it's not empty, or that it's empty if and only if some trivial condition is satisfied, namely, you can find polynomials G sub I such that some linear combination F1G1 plus F2G2 plus FKGK is equal to 1, or so any non-zero scalar, but let's say equal to 1. Because if there were an A on which all the F's vanished, you would have 0 plus 0 plus 0 equals 1, which is an extremely rare occurrence in mathematics. So that's the Nathanson-Polya. And someone, I remember hearing a lecture once in the social sciences seminar at the Institute for Advanced Study, where someone explained how to become famous.
0 equal to 1 is not very rare in mathematics. That often happens when you prove something by contradiction.
Okay.
Yeah.
Okay. Thank you. So, and someone said, here's how you become famous in the academic world. You create a new subject. But if you can't create a new subject, then you put a new name on an old subject. So someone created the following name. Instead of Nathanson-Polya, Positivstellensatz. And a Positivstellensatz tells you if you have, for example, a polynomial in n variables, you want to know if there's some set omega in Cn such that f of A1 up to AN, I want this to be a polynomial with real variables. So this really fits into what people sometimes call real algebraic geometry. So you want to find a set in Rn, omega, or you ask for some set omega in Rn, is this polynomial greater than 0 for all A1 up to AN in omega? And very often for the set omega, you take the non-negative octant. So you look at all A1 up to AN, where the A sub i's are greater than or equal to 0, and but you exclude the 0 vector. So, and the question is, or a question is, how can you recognize if a polynomial takes on only positive values in this non-negative octant? And such a result is called a Positivstellensatz. And as I discovered in the last couple of days, as in almost any other field in mathematics, there was an infinite literature on this subject. And one of the very first results in this subject is an old theorem of Polya, which is very beautiful. And I thought I would describe it. And maybe instead of talking about the Boudin-Fourier theorem, or if this only takes 10 minutes or so, then I will talk about the Boudin-Fourier theorem. But I want to talk about Polya's Positivstellensatz. So you can think of the question as this: you have a polynomial in n variables with real coefficients. How can you tell if it only takes on strictly positive values? And so there's one way that's obvious. So suppose your polynomial, let's call it capital F, x1 up to xn. Then we write it as a sum over, so alpha is going to be some n-tuple of non-negative integers. And so my polynomial is some coefficients, a sub alpha, and let me write, this is x1 to the alpha 1, xn to the alpha n over alpha 1 factorial over alpha n factorial. So this is a general polynomial in n variables. And so one certainly sufficient condition for this polynomial to take on only positive values is if a alpha is greater than 0 for all alpha, that okay, right? I mean, if all the coefficients are positive, maybe just I'll say non-negative, just so I don't have to worry about some little things. So if all the coefficients, if all the coefficients are strictly positive, then if you plug in positive values for the x's, you always get a strictly positive number. If you plug in non-negative values, you might get a non-negative number, but certainly a kind of sufficient condition is the positivity of the coefficients. Okay. So that's clear, right? I mean, if a polynomial has positive coefficients, it's going to be positive for positive values of the variables.
How insistent are you here on distinguishing between positive and non-negative? There's a little bit of fudging here at the moment.
Correct. There is a little bit of fudging, and
so there should be like a finite set of that we're summing over, right? Alpha is ranging through some finite set.
Oh, yes. Yeah, it's a polynomial. So yeah. I'm only summing over certain alphas, a finite set, and the a alphas are all non-zero. But even that doesn't matter, but it's a finite set. It's a polynomial, so they're only finite in many terms. In fact, I'm going to restrict myself following Polya to homogeneous polynomials. So F, I'm going to consider to be an m-ary, n-adic form. Sorry, let me get this right. Some binary, ternary, quadratic form. So the ary is the number of variables. N-ary, m-adic form. So I'm only going to look for, I'm only going to be considering polynomials where the size of alpha, which is the sum of the coordinates, is exactly equal to m. So I'm going to look at forms. In any case, it's a polynomial in n variables, and if the coefficients are all positive, it certainly is going to take on only positive values for well,
no, I mean, you're allowing some of the variables to be 0. So it could be that they just,
right. No, right. So, so that's why I have to, that's why I'm making the condition that it's non-negative.
Well, if you required, but when you were defining the posit, a few lines back, when you were requiring f be strictly larger than 0, if you replace that with larger than or equal to, you'd probably be fine, right?
Oh, yeah, absolutely. That's what yes, absolutely. So I want actually, my puzzlement is on Polya's use of language. Sometimes by positive, I always mean strictly positive. But in ancient times, that is in Polya's time, sometimes positive meant non-negative. So let's say non-negative, and then I don't have to worry, because if you had a polynomial like x1, x2 plus x1, x3, if that was your polynomial, then if you take f of 0, 1, 1, that's 0. So here you have this ternary quadratic form, and this is a non-zero value of the variables, but this gives you 0. So let's just say non-negative, and then I don't have to worry. Right? So in any case, all I'm making is a trivial observation, which is if a polynomial has strictly positive coefficients, it is positive in the non-negative octant. It is non-negative in the non-negative octant. And Polya's theorem is the following. So this is, I'll call this Polya's Positivstellensatz, or theorem for short. If f of x1 up to xn is non-negative on the first quadrant in the non-negative octant, then there exists some exponent k naught such that for all k greater than or equal to k naught, actually, then there exists k naught such that if I take the polynomial f of x1 up to xn, and I multiply it by x1 up to xn raised to the power m minus, there exists a k, raised to the power m minus k. So here I have a polynomial. This is a form of degree m. This is a form, also in n variables, of degree k minus m. So the product is a form in n variables of degree k. And so this is some polynomial g of x1 up to xn. And this polynomial has strictly positive coefficients. And of course, this polynomial has strictly positive coefficients. So if f is a polynomial which takes on only positive values, or non-negative values, for non-negative values of its of the variables, if f is a polynomial which satisfies an equation like this, right? So you have a polynomial f times this very particular polynomial, x1 plus x2 up to xk to the power k minus m. If that's a polynomial with strictly positive coefficients, then f only takes on positive values for positive values of the variables. Because if you choose x1 up to xn, positive, this is positive, because the coefficients are positive. So this has to be positive, right? If something times a positive number is positive, this is positive. So any polynomial which is positive in the non-negative octant satisfies an equation like this. It's not that f has to have non-negative integral. It's not that f has to have positive coefficients. It's that f times some power of this just basic linear thing is going to have positive coefficients. right? That is Polya's theorem, which he certainly did not call a positive Stellensatz, because he was above such a thing, but someone did, and has turned it into a field of real algebraic geometry. All right.
I have a question.
Yes.
What if f is the constant polynomial 0?
Sorry?
If f is the constant polynomial 0,
yes.
What is the constant k?
So the thing is, when I start to prove something, I want to prove it. I'm really for polynomials that are strictly positive in the non-negative octant, right? So this is what I want to say, and excuse the preliminary statements that I made. If f is strictly positive on the non-negative octant, except for the 0 vector, then there's a k bigger than m, such that this x1 plus x2 up to xn to the k minus m, the product of these two polynomials gives us a polynomial which is going to be in n variables and of degree k. Right? So the 0 polynomial doesn't satisfy this condition.
Okay, thank you. Now it makes sense. And I have another question. The
Sure.
degree of the polynomial capital F is the same as the number of variables?
No, no, it's n variables.
Okay.
M degree.
Okay. Okay, thank you. Thank
you. When you say G is positive, does that mean that all the coefficients it can have are positive, or are some of them allowed to be 0?
No, no. If they're 0, you don't see them. So,
I mean, okay. You're just saying no negative. You're just saying no negative coefficients.
Yes. Correct. It has strictly positive coefficients.
Mm-hmm. All the non-zero coefficients are strictly positive. Yeah.
Yes. Yes. Okay. So
my turn to ask question.
Please.
Did Polya determine this k estimation in terms of the polynomial f?
Okay.
Is it effectively computable or not?
Okay, that's a very good question, Henrik, because you are a late 20th century mathematician.
Who asked too many questions. So.
No, who worries about computability and effectiveness.
That's right.
So Polya, you will see that the Polya's proof is not effective. However, in our time, when for reasons that I perhaps understand, not always sympathetic with, people try to make everything effective. If you wanted to use this theorem, if someone gave you a polynomial f explicitly, and asks you, is this polynomial positive in the non-negative octant? You would say, okay, all I have to do is multiply it by x1 up to xn to the power k for some k that I can compute in terms of f and its coefficients. So and there is a large literature making Polya's theorem effective.
Oh, I didn't know.
The one paper that I remember only because I used to know the author, it's a paper, so-and-so and Bruce Resnick, who was a guy in Urbana, whom I used to see when I lived in Illinois. So there's a paper of someone in Resnick, which gives an explicit estimate for this exponent. He improved on a previous estimate by other people, and his estimate was subsequently improved. But there is a literature making Polya's theorem effective.
Okay.
That is definitely the case. Okay. But I just...
How bad are the bends? Just curiosity.
Excuse me?
How bad are the bounds?
So it depends on some invariants that they somehow describe in terms of the coefficients, but don't compute. I don't know how hard they are to compute. I mean, it depends on something simple like, you know, the degree and the number of variables, but then there's some other, there are two other parameters that they use. And, but literally, you know, it's, I sort of came across this a couple of days ago, this whole subject actually. And I looked up Polya's paper because my prejudice is that if Polya wrote a paper, it was probably a good paper. And I spent a tiny bit of time trying to understand his paper. There's one point I'm going to point out, which I don't understand, which anyone who knows advanced calculus can explain to me, or maybe not even advanced calculus, maybe pre-calculus. But what I want to do is prove Polya's theorem, all right? But I mean, you have to think about this for a second. I think this is an amazing result because all you know about the polynomial f is it takes on strictly positive values for positive values of the variables, or non-negative, not all zero values of the variables. And somehow there's this very particular simple polynomial, which is positive in the non-negative octant. And f times this polynomial to some power gives you a polynomial whose coefficients are all positive. So that fact tells you that f is positive. Right?
I have a proposition.
Yes, sir.
Specific case, when f itself is a square, then, I mean, doesn't need to have a square of non-negative coefficients, then what k must be here in order to get that statement, in order to get positive coefficients?
Right. So actually,
f is a square, no other conditions.
Right. So I did the following little numerical experiment. I took the polynomial 2x squared minus 5xy, no, minus 6xy plus 5y squared.
Right.
So the coefficients are, there's a negative coefficient.
Yeah.
On the other hand, this is x minus y squared plus x minus 2y squared. So this is strictly positive except when x and y are 0.
Yeah.
So I took this polynomial and I went to Maple and I multiplied it by x plus y to the, you know, some power. And I was looking to see when I would get all positive coefficients.
Right.
And I never did within the limited amount of time. I mean, you know, you write a little loop, you know, for k from 1 to 100 do. And, you know, and of course, if for some k this is positive, then multiplying it again by a not higher power of this, or just by the, you'll still be positive because you're just taking positive linear combinations of the coefficients. So if it's true for like k equal to 100, it's true for everything bigger than 100. So I was actually going up by multiples of 100, and I never found it. I mean, obviously, I didn't go far enough. But
how far did you go? 1,000 to 10,000? How far?
No, I didn't go up to 10,000. My computer would probably, my old little Mac.
So how far did you go?
Up to, let's say, up to 1,000. I don't remember.
Okay,
but it wasn't a small number. It should have been a small number. I mean, what the hell does effective mean if for something as simple as this, you have to go into the thousands or God knows what? I mean, you know, if you're interested in computability, you might say, well, if I can make it k explicit, is computable, but even that's nonsense because it's, you know, even though you can write it down, it's too big. So in any case, what struck me as beautiful was the theorem of Polya. I think it's an amazing theorem. All you know about F is it takes on strictly positive values. Its coefficients can be positive or negative. You multiply it by this very simple positive polynomial, and you get another polynomial, and somehow all the minus signs disappear, right? Henrik, why should the minus signs disappear? Can you give me a reason why this should be true?
No, that's why I came to listen to you.
Okay.
What were you smoking?
I don't smoke, but I do drink really, really good coffee. Mm.
Okay, you drink, yeah.
Ah.
No, this is one fantastic example showing how difficult it is, you know, to this K.
So
yeah.
So I just went in Mathematica, I went out to 2000 and I'm still getting, and that seemed to work.
Yeah. I mean, oh, was it all positive?
Yeah, let me make sure I'm not.
I mean,
the thing is, are you sure that it's grouping the terms right? Because like it could be sloppy with the like, is there a chance it's not combining all like terms, or definitely?
I mean, the thing was, when I was doing it, I would do it like, let's say to the 100th power. And I thought, oh, it worked. And then I would like but you have like this page after page after page of sums of polynomial terms. And I kept scrolling through it. And then, God damn it, there was a minus sign. So
where did just with x minus y squared, where does it change?
So I'm getting 38. K equals 38 because there are no negatives.
Oh.
For what polynomial?
For the one that's on screen right now.
The 2x squared minus 6xy plus 5y squared?
Yeah. Xy plus 5y squared. We'll have to think about it, right? The sort of off-the-cuff coding is not extremely reliable.
I almost wonder if you're running into some kind of, I don't imagine this would be floating point arithmetic, but when you're talking about to the 1000th power, maybe you're getting some like wraparound or other floating point stuff.
No, actually, let me see if I can do something here.
So Mathematica defaults to arbitrary integer size, so it shouldn't be a wraparound issue.
So I think I just posted this, I just did the calculation in Maple, and it does look like if I take this polynomial and take x plus y to the 38th,
I'm not seeing
these are all positive.
Now, what's wrong with Polya's proof in that German paper?
Nothing.
Oh, so when you just want to understand it, or maybe I didn't follow right. You're saying you want to prove this, but is it it's not proven clearly in the paper? Oh,
it's like I am just giving an exposition of Polya's proof.
Oh, okay.
Yeah, no. I mean,
oh, just the way you started talking now, it made me think like it's proven, but it was baffling. Or no.
The only problem is my understanding of how in 1927, when Polya wrote his paper, he uses whether by positive he means strictly positive or non-negative.
Okay.
All right, that's the only thing. Nothing more than that. And just because for people old enough to have been required to learn at least 2 of French, German, and Russian to get a PhD, I included with the email announcement of the talk, Polya's paper, which is only 4.5 pages in German. And he refers to a previous result in a special case due to Poincaré. And there's a little It's really just one page, but it's 2 pages, half of one page and half of the next page. So you can also read Poincaré in French and see what it was that Poincaré did. So, okay. So I want to describe.
Mel, one. You should
Yes.
You should also read the other paper of Polya in 1927, the one about Jensen's polynomials.
Ah,
it's equivalent to Riemann hypothesis.
Of course.
You missed.
And I remember, Henrik, when I was giving a talk in the seminar last year, yes. You asked me whether I was interested in Polya's paper because of Jensen polynomials and this connection to the Riemann hypothesis and the recent work of Ken Ono and several others on this, which included a extraordinary laudatory article about the paper by Bombieri.
Yes.
Which seemed to me somewhat excessive in its, but in any case, I'm just interested in polynomials. I mean, I'm a simple guy. Yeah. So, okay.
No, the Jensen's polynomials are polynomials.
Sorry?
Jensen's polynomials are polynomials.
Okay, and I have looked at Jensen polynomials, I must say, and if I ever have something worth saying about them, not already known to the army of people who want to solve the Riemann hypothesis, and I have never been conscripted into that army. But if I ever have something interesting to say about those polynomials, I definitely will.
You're not conscripted because there is no war. Not here.
Yes, well, okay. Anyway, Polya's Positivstellensatz. I have to read something, by the way. There's a guy, a million years ago, I was a graduate student and I had some kind of traveling fellowship thing, and I got to go to Cambridge, and I was friends with a guy named Miles Reed. And Miles wrote this very nice book called Undergraduate Algebraic Geometry. And of course, he proves the Hilbert's Nullstellensatz. And he says the following. I don't know if you can read this. The name of the theorem, Nullstelle, which is 0 of a polynomial, and Satz equals theorem, should help to remind you of the content, but stick to the German if you don't want to be considered an ignorant peasant.
All right.
Anyway, so this is the Positivstellensatz. And we start with, as I said earlier, a M-ary n-adic form. This is a polynomial in n variables, homogeneous of degree m. So I can write this as sum over alphas. And I'm just following Polya's notation in case you do look at or have looked at his paper. So alpha is an n tuple of non-negative integers, which sum to m. And I'm writing the polynomial in this sort of standard way.
Mm-hmm.
And what? Yeah. And
there's several alphas. It's not one alpha.
Well, alpha without a subscript is an n tuple, and the coordinates are alpha 1 up to alpha n. So this is x1 to the alpha 1, x2 to the alpha 2, up to xn to the alpha n. Okay. So this is just a polynomial.
And that's being divided by that's being divided by alpha 1 factorial, etc.
Yeah.
Okay. The exclamation points were a little unclear thanks to the nature of the camera.
Okay. And this polynomial has the property that if you choose variables xi non-negative and not all 0, so the sum is positive, that f evaluated at this n tuple is strictly greater than 0. Okay. And one particular such polynomial is if I take the polynomial x1 plus x2 up to xn, so that's raised to the power k minus m. So this is a form of degree k minus m in n variables. And if I expand this by the multinomial theorem, I get exactly this. The betas are, beta is an n-tuple, beta 1 up to beta n, where the sum of the betas is k minus m. And this is x1 to the beta 1, x2 to the beta 2, xn to the beta n, times the multinomial coefficient, which is k minus m factorial, divided by beta 1 factorial up to beta n factorial. Okay. All right. Now, here is my pre-calculus question that I'm going to need some help with later. But at this point, let me just say that if I take f, this is my polynomial f, and I restrict it to the n simplex. So this is all the points in Rn with non-negative coordinates that sum to 1. So this is a compact set. So f on this is, it's positive, right? Because this is a positive polynomial. So the inf is some number mu strictly greater than 0. Okay. Okay, hope so. All right, now, again, this is my polynomial f. I just wrote it down again. It's a polynomial of degree m in n variables. And now I change it slightly to have a polynomial phi in n plus 1 variables, x1 up to xn, and this new variable y, but still homogeneous of degree m. So it's the same coefficients. And instead of the product, x1 to the alpha 1, x2 to the alpha 2, and so forth, for each xi, instead of xi to the alpha I write xi minus yi, xi minus 2, xi minus y, xi minus 2y, xi minus 3y, down to xi minus alpha I minus 1 times y over alpha 1 factorial, okay? So I have f, and then I perturb it slightly with this y, and I get this polynomial phi. It's again, it's a form, is homogeneous of degree m. And it has this simple property that if I let y equal 0, this numerator just reduces to xi to the alpha I. So phi at x1 up to xn with y equals 0 is just my original polynomial f, okay? So here's my pre-calculus question, if you like. So I know that the inf of f restricted to this n simplex, right? This is the n simplex, is some positive number. So, and phi evaluated at y equals 0 is just f. So I want to say that there's some eta greater than 0, such that if y is between 0 and eta, and the x's lie in the simplex, then phi of x1 up to xn and y is bigger than a half mu, is bounded away from 0, okay? All right. So, but this is an important fact in Polya's proof. Okay. So again, I'm writing things down over and over again, just so they're clear. So this is my function phi of x1 up to xn and y. It's this function. And in particular, if I choose non-negative real numbers, gamma I, gamma 1, gamma 2 up to gamma n, which sum to k. So gamma 1 up to gamma n is some n tuple of non-negative integers. and its weight is k. Of course, if they sum to k, then the sum of gamma I over k is 1, right? And if I evaluate this polynomial phi at gamma 1 over k, gamma 2 over k, gamma n over k, and 1 over k, so I just plug in those numbers here. So I have the sum of these coefficients, product, I goes from 1 to n. I have 1 over alpha I factorial. And here I have, for any given I have gamma I over k, gamma I over k minus 1 over k, which is gamma I minus 1 over k, gamma I minus 2 over k, down to gamma I minus alpha sub I minus 1 over k. Right? And as I plug this in, and this is what I get. And I can take out all of these powers of k that are in the denominators. They're k to the alpha I of them for all I. So I get a k to the summation alpha i's. The sum of the alpha i's is m. So when I pull out all these k's, I get 1 over k to the m. This coefficient, and I have, what do I have here? I have gamma I down to gamma. I have exact over alpha I factorial. This is just the binomial coefficient gamma I choose alpha I. Right? So when I evaluate phi at this n plus 1 tuple, I get this. And these sum to 1. If 1 over k is less than eta, all right, or in other words, if k is big enough, bigger than 1 over eta, then this expression is bigger than a half mu, which is some positive number. Okay, so that's it. All right, so let's just keep that fact in mind. And now let's see what we have. Remember, what I want to show is if I take this positive polynomial f and I multiply it by some power of x1 plus x2 up to xn to the k minus m, if I multiply these together, I will get a polynomial with positive coefficients, right? If k is large enough, that's the miracle. So f1 up to xn, f is this polynomial over alpha with coefficients, the a's, and I have x1 to the alpha 1 and so forth. I have xi to the alpha I over alpha I factorial. That's what f is. And when I expand x1 up to xn to the k minus m, again, this was just the multinomial theorem. I get k minus m factorial. A sum over these betas, these are n tuples that add up to k minus m. I get x1 to the beta 1, x2 to the beta 2, and so forth. Here I'm just combining x1 to the alpha 1 times x1 to the beta 1. So it's x1 to the alpha 1 plus beta 1 for and so forth. And these beta 1 factorial up to beta n factorial. I mean, this is the multinomial coefficient. So this is just taking the series for f, the series for this, you multiply them together formally, this is what you get. And let's see, if I want to rearrange that slightly, this is this doesn't change. So if I take alpha 1 plus beta 1 factorial over alpha 1 factorial beta 1 factorial, that's this binomial coefficient. But I put an alpha 1 plus beta 1 factorial in the numerator, so I have to put it in the denominator so nothing changes. So when I do that for each of these terms, I get this expression. And now the sum of the alphas is m. The sum of the betas is k minus m. So the sum of the alpha I plus beta i's is equal to k. So if I look at the vector whose coordinates are alpha 1 plus beta 1, alpha 2 plus beta 2, and so forth, that's some vector gamma, the sum of whose coordinates is k. So I can write this is k minus m factorial. Here I'm summing over n tuples of gammas that sum to k. I have alpha 1 plus beta 1 is gamma 1 and so forth. I have x1 to the gamma 1. These are the gamma I factorials. I have, this is gamma 1 over alpha 1. These are I just get exactly this. All I've done is write gamma I as alpha I plus beta I. And this is a sum over just certain gammas. But if I take any vector gamma and write it as alpha I plus beta I, where alpha I plus beta I is gamma I, if it's not one of these, then the alpha I is bigger than gamma I, and the binomial coefficient is 0. So I'm really just summing over all gammas here. This is perfectly legit. And what do I have here? So this expression, what is that? I thought I had that a minute ago. Wow, I did. A minute ago, this expression is phi of gamma 1 over k up to gamma n over k 1 over k. That's what this is. So, and this is a polynomial. And if k is bigger than 1 over eta, this is a positive number. Right? This is strictly positive. And this is positive, and this is positive. So this right-hand side is a polynomial in n variables, homogeneous of degree k, again, with only positive coefficients. So that is the miracle of Polya's proof, right? If k is sufficiently large, f times this linear form raised to the power k minus m gives me a polynomial with positive coefficients. And the only condition is that f takes on strictly positive values in the non-negative octant. Okay, well, that's it. That's Polya's theorem. And I would say it is a fantastic result. I mean, it's just beautiful to me, because I don't know why anyone would guess. Now, of course, Polya had an advantage. He read Poincaré. There's some preliminary works, special cases that might have suggested this. But in itself, I just find this an extraordinary theorem. You take a polynomial which is positive in the non-negative octant. And another way of saying this, which is reminiscent perhaps of Hilbert's problem about rational functions that are positive and being therefore sums of squares of rational functions. Another way of saying this is, if you take a polynomial f, which is positive in the non-negative octant, you can write it as a rational function, a quotient of polynomials, where both the numerator, that's this, and the denominator, that's it, are polynomials with strictly positive coefficients. So if you have a rational function whose coefficients are all positive, and you evaluate this, you're going to get a positive number. Or sorry, I should let me say that more carefully. If f takes on positive values in the non-negative octant, then it can be written as a quotient of polynomials with positive coefficients. That exactly is Polya's theorem. All right, so since all you savvy people have taken calculus at some point, what is the baby argument that I am missing to explain this pre-calculus statement? That I have this polynomial, this function f, and if the x's are in the simplex, when y equals 0, it's bounded away from 0 uniformly for every point in the simplex. So there's actually some neighborhood around 0 where if y is in that neighborhood of 0, this is also bounded away from 0. Right? Why is that?
It's just I think it's just a continuity argument.
Yes, of course. What is the argument?
Compactness.
What?
Compactness. That's where sometimes you have ineffective bounds, but here you can get the compactness, right?
What is, I mean,
no, I mean the
simplex is compact.
The set f of x1 xn on the simplex, right?
Right.
It is a
right. It's bounded away from zero by compactness.
Pardon? Well, of course, a huge large value. You can use compactness because you can eliminate extremely large values of x's, right?
No, I'm just living on the simplex.
Anyway, I probably shouldn't challenge the calculus classes. Yeah.
Well, the only way I know to really solve this problem is if I were making up the analysis prelim at the grad center, I could put it on the exam and someone would solve it for me. But
Mel, I know shorter proof.
Of Polya's theorem?
Yeah.
Okay.
By eliminating some of your lines.
That will do it.
Yeah, you gave too many details, actually.
Okay. Since I have a couple of minutes, let me actually say something about what was supposed to be the subject of this talk, which is the Boudin-Fourier theorem. So the Boudin-Fourier theorem is the following. This is now for polynomials in just one variable. So f of x is a polynomial with real coefficients in one variable. And if its degree of f is n, it has n complex zeros, but we want to know how many real zeros there are. And in particular, suppose we let z sub f of a, b be the number of lambda in this half open, half closed interval from a to b, such that f of lambda equals 0. And we want to figure out what this is. Suppose I let z sub f c of a, b be the number of lambda in the complex numbers, where the real part of lambda, or let's say the number of z in the complex number, so the real part of z, which I'll call lambda, is in this interval from a to b, right? So what we know is that the number of complex zeros equals the number of real zeros. And because this polynomial has real coefficients, the complex zeros occur in complex conjugate pairs. So the number of real zeros is some even number. I'll call it 2n0, okay? So if I knew what this was, I could say that the number of real zeros in this interval from a to b is this number minus a non-negative even integer. Right? Of course, I don't know how to find that number generally. And the Boudin-Fourier theorem says the following. There is some number v. So if I take a sequence of numbers, x0, x1, up to xn, so these are real numbers. This is the number of sign changes in the sequence. And by sign change, I mean ignore any of these which happens to be 0. So as you go from left to right, a sign change is when you have a positive number, maybe some zeros, but then a negative number, or a negative number, and then maybe some zeros, and then a positive number. So ignoring the zeros in this sequence, the number of sign changes in the sequence, that's what this means. So if I take a polynomial f, and I take v sub f of some number x, this is going to be the number of sign changes in the sequence of f and its derivatives up to the nth derivative, right? So VF of f, V sub f of x is the number of sign changes in this. So the Boudin-Fourier theorem says that VF of A minus VF of B. So I look at this at A, calculate the number of sign changes. I look at this at B, calculate the number of sign changes. This is going to equal the number of real zeros of F in this half open interval from A to B, plus some non-negative even integer. But this I can calculate because these numbers, I mean, basically all you have to do is write down the Taylor polynomial for F with center at A and center at B, and up to a positive number, a factorial. These are just the coefficients of the polynomial, the Taylor coefficients. So I can calculate these. I look at the number of sign changes here and here, look at the difference. Somehow, by some miracle, this is always greater than or equal to this, because you can't have a negative number here. And this is equal to the number of zeros plus an even integer. And this I can calculate, okay? So that's the Boudin-Fourier theorem. And I am curious whether, so, well, of course, there's several questions. What is this? Right? What is it? I mean, it's a number. I mean, if this turns out to be 1, then over here we have a number plus an even integer that's not negative is 1. So if this is 1, this has to be 1 and this has to be 0. Or more generally, if this difference is odd, then the number of real zeros must be at least 1. There has to be a 0 between A and B. If this number is even, you don't know anything. But in any case, you get that there is some number, and how do you interpret this? Now, on the principle that nature abhors a vacuum and the mathematical literature abhors vacuums, there are several papers written describing what are called virtual zeros of a polynomial. And this difference on the left-hand side is equal exactly to the number of virtual zeros, which are all the actual zeros, plus some other things which you count here. And I have looked at some of the papers on virtual zeros, and I know what properties they satisfy, but I can't figure out what they are. And I'm not sure if the notion in the literature of a virtual zero, which is just a way to explain this term, is the best way to understand this term. So that, for me, is an interesting question in polynomials, or if you like, real algebraic geometry. But I'm also interested in this. I don't know if there's some algorithm or some method that allows you to calculate the number of zeros in a polynomial in some vertical strip in the complex plane. You have the strip from A to B, and you want to know how many zeros are there in some easy to calculate way. I mean, I don't know if there's some, Fragment-Lindelof theorem or something that does that, but I don't know. Anyway, that's the little I had to say, or will say today, because I'm done. Anyway,
thank you.
That's the story.
Appear in literature, like in Matiasiewicz's theorem, right? It's he constructed a polynomial in many variables with the property that all positive values are just prime numbers. But it's a little bit different thing.
Yeah, a little bit different.
Yeah. So there is some interest in this. I mean, coming back to Polya and the Jensen polynomials, as you said, the huge literature and fascination. Bombieri wrote an article, but also Kenono, Zagier, and I think many other people. And Turan, by the way, also, right? The Hungarian school, yeah. And it's amazing that, you know, the Riemann hypothesis is equivalent to hyperbolicity, right, of these polynomials, which means polynomials which have only real zeros. And the polynomials are just obtained by power series expansion of this, you know, normalized zeta function on the critical line, right? And yeah, okay, whatever. I mean, you can talk endlessly about it, but it's not related to what you said today. Nevertheless, it was a very nice talking, man. I didn't know that theorem.
Oh.
No, I didn't. Yeah.
Okay, everyone.
If I may, I was just going to say, I think thanks to Professor Vanitz's idea about compactness, I think I managed to figure out the bounding that you were asking about. Essentially, we can restrict phi to that simplex cross, maybe the closed interval from 0 to 1 for the y variable, and then that's compact, and we know that it's going to be continuous on a compact set, so it'll be uniformly continuous. And so, in particular, for epsilon equals like 1/2 mu, we can always find a some epsilon such that if like the vector consisting of the inputs such that if such that we can always find a delta such that if x1 x2 through y and then x1 prime x2 prime x2 prime through y prime, if the distance between those is less than delta, then the distance between the outputs of the polynomial will be less than epsilon, which is 1/2 mu. So in particular, for any y that's less than delta, we have that phi of y, the phi of x1 ... xn comma 0 minus phi of x1 through comma x2 dot it's dot dot
I understand what you're saying.
Yeah.
I mean,
I think that works.
Right. Yeah. I mean, I was trying to put together some sort of argument like that, but didn't. Okay. Questions, comments?
Sorry, I have to leave. You know, it's too late for me. Bye. So see you next time.
Shana Tova for all to whom that makes any sense. And we will be back a week from today on Zoom.
Wait, so we're meeting next week, even though it's a Monday?
Yes, we're just not allowed to meet in the Graduate Center.
Okay.
Via Thursday.
Yeah, for most of the world it's Thursday, but in the narrow precincts of the City University of New York, we follow a Monday class schedule.
Yeah, all right. I won't be able to make it. I have classes on Monday.
Do you really?
Yeah.
Oh my God. Okay, well then we'll have to prove the Riemann hypothesis or something, just so
What's the recording?
Okay, everyone, be well.
Thank you, Mel. All right,
Thank you.
thanks very much.